Gavin, you spend a lot of time on this boat out in these waters. Tell me what your job is.
My job at Plymouth Marine Laboratory is to take optical data to ground truth satellite, particularly ocean colour.
And that's quite an involved job because satellites produce lots of numbers, lots of data, but it isn't useful by itself, and that's part of what you do.
Yeah, every day we get images in near real time that we process up, but some of those images are obviously cloudy, so obscured by clouds, and also this is a dynamic area with very changeable conditions, so we've got different influences from the river, from depth in terms of suspended material, and so we need to take as many measurements as we can to characterise the optical properties in this dynamic location.
And there's this very specific word associated with the satellite work, which is validation. Explain to me what validation means.
Validation is where we go out to the ocean and we take the ship out at the same time that the satellite is overpassing. And at that moment, within a window in the coastal zone, it's plus or minus 30 minutes. In the open ocean, it's longer. At that exact time when the satellite is orbiting, we deploy our instruments into the water to measure the inherent optical properties, the apparent optical properties, and we take a series of discrete measurements to characterise the phytoplankton and the other optical components in the water column.
So the idea is that you're measuring everything about the water in the water, and then you can cross-check that with what the satellite sees when it's going overhead, so you can make sure that you understand what the satellite measurements mean.
Yes, exactly. I mean, it's very variable, so if we go further out there onto the shelf, then we might just have phytoplankton that is the dominant optical component. But as we go over here, more towards the coast and towards the river, we've got plumes of coloured dissolved organic material that absorb light at the same wavelength as the phytoplankton, so they obscure the signal from the phytoplankton. So we have to go to these different range of environments, different places along the coast where you might have different signals from different components, so that when we're back in the lab we can decompose the signal from each of those components, and we can develop algorithms to be able to sense these different components.
And so the key thing here is that when you scoop up a bucket of water down from the ocean here, it has properties, optical properties associated with it. What that means is that the way light travels through it is different for different packets of water, and that's what you really want to get at from the satellites, because that's where the information is.
Yes, exactly. I mean, we've got a whole different array of phytoplankton that will absorb, because of their pigment array, the type of pigments that they've got, they will absorb light at different bands. And we've got coloured dissolved organic material that absorbs highly into the blue, so at the same peak wavelengths that the chlorophyll pigment is absorbing at. But we've also got detrital material that also absorb into the blue, and we've got suspended material that scatter the light and also mask that absorption. So we've got to be able to differentiate between all these different components and, if possible, the different phytoplankton themselves.
And tell me about the satellites that you've been involved in validation for.
So I've been involved in a whole gamut of satellites, from SeaWIFS, which was launched in 1997, to the European Space Agency satellite MERIS, and now I'm working on Sentinel, particularly Sentinel 2A and Sentinel 3A. Sentinel 3A was only launched in February, and this is going to be the primary satellite, ocean colour satellite, now for the next 20 years through a series, 7-year period of 3 phases, which will become the primary ocean colour satellite for the foreseeable future. So it's very important that we ground truth this data to know the quality of the data for end users. These bottles are continuous tubes that have automatic releases which are linked to the computer on the bridge, and at any determined depth they can be fired automatically from the keyboard to close the bottles. So as they go down in the water column, the water is passing through the bottle, and then the instrument is settled at depth, and then from the profile, from the temperature, fluorescence and salinity, we can choose whichever depth we want, which can be fired automatically from the bridge.
So Gavin, we've got some data here which is typical of what a CTD might measure. Tell me what we're looking at.
We've got 6 different parameters on this screen. So in red here we've got the temperature of the water column.
So we've got, this is depth through the water.
Yeah, we've got depth here. This is going down to 70 meters. And the temperature shows that we've got a mixed layer to about 10 meters, then it stratifies down to 20 meters, and then below 20 meters it's mixed again because of this straight line.
So even though we think of liquids as mixing quite easily, out in the ocean, this is actually quite common. You get a top layer that's pretty much the same temperature because it's all mixed in together, but that's separated from the next layer down, which is a different temperature, and then layer below that. So this is quite a common pattern. So that's very important then. The satellite data isn't just about what's happening right at the surface, it's also an indication of what's happening underneath.
Yes, I mean, at different times of the year you're going to see a different structure here. I mean, this is a typical summer structure where you've got some stratification. In the winter, for example, it might be completely and thoroughly mixed. In the spring, you may have a surface bloom of phytoplankton, and so the fluorescence trace will show a peak here. But then later in the summer, you may get a subsurface trace. And of course, we need to characterise this temporally in order to then use the data to build other models which we can use the satellite for.